Good afternoon, everyone. Welcome to this seminar titled A New Space Race is Just Beginning, but Will It Be Safe? My name is Anne Green, and I'm Chair of the New South Wales Division of the Australian Academy of Technology and Engineering, ATSE, and I'm delighted to welcome you all to this function organised jointly with the Academy and with the Union University and Schools Club. And this is a hybrid session, so we're partly online and partly in the room. In the spirit of reconciliation, I'll begin by acknowledging the traditional custodians of country throughout Australia. We pay our respect to their elders, past, present and emerging, and extend that respect to all Aboriginal and Torres Strait Islanders present today. As we share our own knowledge, I acknowledge the most ancient and enduring knowledge in the world, embedded forever in custodianship of country. We're joined today by fellows of the Academy of Technology and Engineering, members of the Union University and Schools Club, as well as friends, collaborators, partners, both in Sydney and more broadly. ATSE is a learned academy of independent experts, and our fellows are among Australia's leaders in applied science, technology and engineering. They come together to provide impartial, practical and evidence-based advice on how to achieve sustainable solutions and advance prosperity for our society. So welcome all. Now the logistics, I should give you a few logistics for today. The technical organisation is via the Secretariat of ATSE and the Union Club Administration, and I thank them for their assistance. We have participants online and in the club premises. All online people will have their audio and their videos muted centrally during the talks. However, there will be plenty of time for questions afterwards and comments through the Q&A function, please. And then we'll also have questions from the participants in the club. The webinar is being recorded and the video will be placed on the ATSE website. So let's start. Over the past 50 years, there's been a rapidly growing interest in space, in discoveries, travel, technology, and ownership. There have been remarkable recent developments such as extraordinary images and discoveries from different extraterrestrial missions, the possibility of a manned visit to Mars, and thousands of commercial microsatellites which are due to be launched into orbit. We are at the dawn of a massive increase in the use of man-made satellites for a multitude of issues. So it's my privilege to begin today's seminar. Small introduction, I'm Emeritus Professor of Astrophysics at the University of Sydney, a radio astronomer of several years, who's been studying the structure and ecology of our galaxy, the Milky Way. I'm interested in violent events, the relics of supernova explosions, celestial mazes, and more recently, powerful bursts of radio emission of unknown origin coming from vast distances. I've held several leadership positions in astronomy nationally and internationally, and I was privileged to be the first female head of the School of Physics at the University of Sydney. I'm also a fellow of ATSE, the Australian Institute of Physics, and the Astronomical Society of Australia. So let me begin by sharing my screen. This picture of the night sky, a very famous part of the night sky shows the Southern Cross, but what I want to draw your attention to is the star, the little yellow star, you can see my cursor on the left. That's Proxima Centauri. Well, it's actually Alpha Centauri, which is a triple system, including Proxima Centauri, which is the closest star to us. Now that star is close, but it's still 4.24 light years away, which is something like 40 trillion kilometers. So when we're talking about missions to places other than Earth, we're never going to get there, at least not as humans. However, that certainly is the focus of one of the new space missions called Breakthrough Starshot, which is a concept to try and use an array of lasers to power a fleet of microsatellites. So that's one end of the scale. The other end is we actually send humans somewhere. So let me now continue. And what I'm going to talk about today, some of the things I'll cover is to go back to and tell you about the start of the space race. Satellites have enabled many discoveries. How many satellites and where are they? And is space getting overcrowded and should we be worried? So what I'm not talking about is the big questions. Are we alone? Where did we come from and where are we going? I think that's for another time. So let me start now with the space age. It begins on the 4th of October 1957 with the launch of the first artificial satellite from the USSR. So this was Sputnik 1, 58 centimeters in diameter. So that's not very big. It weighed 84 kilos and its battery lasted 3 weeks. It was in orbit for about 3 months and then it was deorbited. I'm not even sure that's a word, but it was deorbited and burned up in the atmosphere. It was transmitting at 20 and 40 megahertz, which bands for amateur radio. And so there were a lot of radio aficionados who actually were tracking Sputnik 1. So that 3 months later, it disappeared. So some early successes in the space race. 1961, USSR put the first man in space, Yuri Gagarin, and in 1963, the first woman in space, Valentina Tereshkova. 1969 was a day that most of us will remember, first men to land on the moon, Neil Armstrong and Buzz Aldrin. But in between that, in about 1966, both Russia, or USSR it was then, and the USA were doing soft landings of equipment on the moon. So in fact, there's a lot of debris and a lot of stuff sitting up on the moon. 1971, Mariner 9 landed a probe on Mars. So that was the early start. Since then, there have been lots of missions. One very famous one is Voyager 2, which was launched in 1977, took 7 years to get to Saturn, and is still going, and it's now beyond the solar system. So this is a beautiful picture taken by the Cassini-Huygens probe, which was launched in 1997. 4 years later, it got to Saturn. And then it was doing experiments and observing Saturn and its rings. So you can see where that head of the arrow is. If you have good eyesight, there's a little dot. Now I've blown that up. And that pale blue dot is Earth. So this image is famous, and it's called The Day the Earth Smiled. And in fact, Saturn is blocking the sun's rays. That's how you can actually see that little dot. Cassini was in operation from 2004 to 2017 when it was, on purpose, plunged into the atmosphere and the surface, such it is, of Saturn. So that's a bit further out. Let me now talk about satellites going around the Earth. So most of them are what they call low Earth orbits. They're above the atmosphere, which is about 100 kilometers, and below the inner of the Van Allen belts, which last from about 160 to 2,000 kilometers altitude. So the low Earth orbit satellites have a speed about 10 kilometers a second. To give you some idea what that means, that's 10 times the speed of a bullet. So it's fast, and if you got hit by something like that, it would do a lot of damage. Typically, low Earth orbit satellites have polar orbits and a period of about 90 to 100 minutes. So the next, and what low Earth orbits are used for, communications, it's the region where the International Space Station is. Iridium GPS satellites, that network is also there. You can see on the lower left, this is GPS satellites. They have an altitude of about 780 kilometers. Then further out, we have the geostationary orbits, and they have an equatorial orbit around the equator of about 35,000 kilometers altitude. And they're used principally for weather forecasting and also for television. And they have sensing in both the visible and infrared imaging. There's also another kind of satellite that has the name GEO. It says they're geosynchronous orbits. And those ones have an orbit which is connected to the sidereal day. So they wobble up a little bit and down around the equator. So the geostationary satellites have a speed less than the low Earth orbit ones, about 3 kilometers a second. And of course, as the name says, if they're geostationary, then their period is 24 hours. So it's a rather complicated plot. but it actually has got a lot of information. It shows up here the orbital period, and as I said, the geostationary ones are in lockstep with the Earth's rotation. The inner ones here, this is where the International Space Station is, and the Hubble telescope, Iridium. The GPS is around 780 kilometers altitude. And this plot also shows you then the radius of the orbits. I told you geostationary satellites are around 35,000 at least kilometers altitude. This is the radius of the orbit from the center. This is then the altitude, the height above sea level, and then the orbital speed. So this doesn't have it in kilometers a second, has it in kilometers an hour. So the geostationary satellites are traveling about 11,000 kilometers an hour. As well, there's a succession of military satellites which are around in the middle part, and there are some highly elliptical orbits. So there's a lot of satellites up there. So the question then is, how many? How many satellites? So between the launch of Sputnik in October 1957 and March of this year, about 9,500 satellites have been launched from over 40 countries. 9,500. But of those in orbit, only 2,666, and this number comes from March 31st, 2020, are operational. So there's a lot of dead satellites up there. Most of the satellites are low Earth orbit, 63%, and about a third are the geostationary ones. So this data comes from the Union of Concerned Scientists, and of the operational satellites, the majority just are from the US, about 350 are from China, 170 or so from Russia, and nearly 1,000 from all the other countries. And of the US satellites, the vast majority are commercial. So what else is up there? It's what we call space debris, and there's a lot of stuff. Now remember that something traveling at 10 kilometers a second is traveling at 10 times faster than the speed of a bullet. So if something hits you at that, it does a lot of damage. So what's there? Dead spacecraft, rocket booster and launch parts, drops of coolant, lost equipment from various space walks, a camera, there is garbage bags, there are tools, there's a wrench, toothbrush, a glove, and paint flakes. So there's also debris from anti-satellite weapons testing. And I'll get to that in a minute as to when that happened and what we're doing about that now. There's also a lot of in-orbit collisions, which create far more fragments. And there's something called the Kessler syndrome. So this is basically saying it's the cascade effect. And the prediction is that in 20 to 30 years, most of the debris will come from collisions of stuff already orbiting, and it will cascade so that that cascade of new parts will exceed the losses from orbital decay, in other words, things falling back to Earth, and will make some orbits pretty much unusable. So this is a picture of what, it's an art simulation of what it looks like from space. And this is the low Earth orbit debris. So let me now talk about some examples of stuff which has fallen back to Earth. Remarkably, there hasn't been anybody killed by falling debris, and partly it's because we have what's called a spacecraft cemetery in the South Pacific Ocean. And so for those parts, both craft and anything that can be steerable, they then try and organize so that when they come back through the Earth's atmosphere, if they are too big to burn up, that they will land in the South Pacific Ocean. But you can see that something landed in the Arabian Desert, a rocket module in 2001. This one picture up here is what happened when the space shuttle got hit by something quite small. This is a Skylab oxygen tank which landed in Western Australia in 1979. And I should tell you about this one. So the Vanguard, satellite was launched in the early 60s. The signals were lost, so it became a dead satellite in 1964. But it's going to, because of its orbit, it will be in orbit for another 240 years. liable to collide with things, and it can't be brought down. So now the question is, how much stuff is up there? So 34,000 objects bigger than 10 centimeters, bigger than this. 900,000 objects between 1 and 10 centimeters size, and 128 million small stuff, less than 1 centimeter. Now those numbers are from January 2019. From 2020, how much mass is up there? About 8,000 tons worth of stuff, but 98% of that are in objects greater than, with a mass of greater than 100 kilograms. And the Space Surveillance Network tracks about 22,000 of these objects, of course, mostly the big ones. So before 2007, most of the debris came from explosions, so rockets, bits that blew up, or spacecraft that blew up. But in 2007, China destroyed one of its non-operational weather satellites, and this was an anti-satellite weapons test, which sent a shockwave literally around the world. And so one of the things that is still to be decided is some kind of a global agreement on anti-satellite weapons testing. And in 2009, two satellites collided, Iridium-33 and Cosmos 2251. And they collided in the low Earth orbit area, and all of these collisions, each one creates thousands of objects. So how do we track this? How do we know what's up there? So they do some tracking from space called long duration exposure, and they actually deploy a satellite to track and to map things, and then that is then brought back and retrieved for study. That's not the most obvious thing, and it's not doing the biggest tracking. So there are two ways that things are tracked from ground. Using lasers, and this is good for very distant, for objects which are in the geosynchronous and the very large orbits at 35,000 kilometers. It's limited by weather because you need sun for illumination, but it's accurate for small debris. And they use a processor called, a system called LiDAR, laser imaging detection and ranging, and it uses optical wavelengths. And then the other way is using ground-based radar, which is better for the low Earth orbit satellites. Of course, it can operate day and night, and there are a couple of options. You can either use one telescope, or you can use bistatic radar using two telescopes, one transmitting and one receiving. And you can see on the left here, this is a radar image of the Mir space station. So Mir space station was put up by the Russians. It was actually assembled in space. It had an altitude of 360 kilometers, and it was there from 1986 to 2001. And in 2001, it was deorbited and it was burnt up in the atmosphere. So you can see in the map on the right that there are quite a lot of stations, some of them doing tracking radar, some of them detection radar. So these colors here are all the radar ones, and then there's also the optical ones. The yellow dots are optical. So what about space travel in the future? Since 2010, there have been a lot of private companies in the field. So instead of government-sponsored space flights, there's been a lot of investment in space flights, in space transport, in space tourism. SpaceX was founded by Elon Musk in 2002, and it is now used to resupply the International Space Station. Part of his project is the Starlink constellation. So he is now launching small satellites, 60 satellites per Falcon 9 rocket launch. And in August 2020, so August of this year, already 655 had been launched. So the plan is to launch at least 12,000 of these in 3 shells, and they're all pretty much low orbit. But these, at the moment, the plan is for 7,500 satellites to be at 340 kilometers altitude, another 2,000 to be around 500, and then the same number around 1,000 kilometers. So that's a lot of satellites. And there is a plan on the table to have up to 42,000. I'm an astronomer, I have to say. If you look at the picture on the right, we're not too pleased. So there'll be some discussion, I believe, and some negotiation, because you can see what a whole lot of satellites, imagining 42,000, what they will do for optical astronomy at night. So, space frontier, what's next? And should we be concerned? I've already said that so far nobody has been killed by bits of stuff falling out of the sky. However, we do need a space code of conduct. It's not the Wild West up there, and destroying satellites just creates more debris. Space weapons testing needs regulation, and so far there is no international treaty minimising the debris. For example, the space station and any crewed missions, or any mission that has satellites with people on board, those missions are aborted if the chance of a catastrophic collision is less than 1 in 200. And if you recall, some years back, the Hubble telescope needed to be repaired, and that mission almost didn't go ahead because of the possibility of colliding with space debris. The International Space Station has a shield against small debris, but it actually moves and maneuvers to avoid big objects. So the next space race that's beginning is Mars. Eventually, possibly, we will send people to Mars. But right now, in July, the 19th of July, the United Arab Emirates launched HOPE satellite to do atmospheric studies of Mars. On the 23rd of July, China launched the Tianwen-1 satellite, which to land on Mars and study geology and do a surface survey. And on the 30th of July, the USA launched the Perseverance rover, which is going to do, again, a lot of geological work and also look for microbial life. All of these satellites will arrive in Mars around February 2021. So, yep, it's getting crowded. Should we be concerned? We need to at least have some treaties and have some I guess, regulation so that we do not block all of the orbits or even the large fraction of the orbits, because we are increasingly using space and satellites to do all kinds of monitoring and surveying and communications on Earth. So I will stop at that point. And now I would like to introduce Eva Cairns. And Eva is a professor in space science at the University of Sydney with over 30 years' experience in several areas of space research. He's co-investigator on NASA's dual solar probes, the STEREO mission, and on NASA's 2 small Explorer missions. So Eva's leadership roles are in Asia, Oceania, Geosciences, in the society there, on the Committee for Space Research and the Space Physics Group of the Australian Institute of Physics. Within Australia, he has a prominent role. He's chaired the Academy of Sciences National Committee for Space Science, and he works hard to convince the government to invest in the space sector. He's led the Inspire2 CubeSat project, which successfully launched in 2017, and currently Eva leads KUAVA, the ARC Training Centre for CubeSats, UAVs, which are unmanned something or other vehicles, unmanned aerial vehicles and their applications, which is training people, solving research problems and working towards commercial outcomes. So please, I would really like you to welcome Eva and have him share his screen.
Well, thank you very much, members of the committee, including Anne and Peter Tyree and Ron King, I think, Peter King, sorry, for inviting me to give this presentation.
We're not seeing. I need to see you a bit more.
Ah, well, you don't necessarily need to see me. Oh, see, okay, so, so that's fine, okay, because I can see Anne, but I can't see the thumbnail sketch of myself, which is possibly good. So yes, thank you very much for the invitation to be here. It's a great pleasure, and it's a great pleasure to be following Anne Green, who was my head of school for a number of years and was responsible for promoting me to a professor in space physics. So hopefully you won't blame her for that after this presentation. But what I was wanting to do was follow on from Anne and talk about space itself and why we as Australians should be involved in it. You know, why is it important? And beyond that, what sort of research and work should we do in space? What sort of satellites? Should it be a 100-ton satellite, you know, which is 10 meters on a side? Should it be very small satellites like CubeSats, which are built of blocks of 10-centimeter cubes? I'll also talk about other risks than Anne. You can see here on the lower left, the satellites that are in orbit at the moment, at least close to low Earth orbit. But, and the debris is, you know, is an issue, but I can come to that later on. But I think there are more important issues to do with space weather, for instance. About 160 years ago, in 1859, the Carrington event occurred, which if it occurred today, it's predicted it would have taken out the American East Coast power grid for up to 10 years. $1 trillion worth of economic damage alone for each of the 10 years required to replace all of the transformers on that. See? And in Iraq war is of order $1 trillion. So absolutely huge amounts of money. And you can also imagine the enjoyment of living on the East Coast of the United States, or in China for that matter, during the summer without air conditioning, without refrigerated food, with everything being just in time, manufacturing and delivering. Human society, arguably, would go back to the Stone Age. And I would argue that that's a more important risk for us to worry about than space debris, at least at the moment. So I'll talk a bit about those aspects. I'll talk a bit about CubeSats. You can see one in the center of the screen here, 2-unit CubeSat, 20 centimeters tall. That was my baby for a number of years. I held it in my arms. I put it into a vibration machine that vibrated at equivalent of 10 Gs. One of the hardest things I've ever done, because you hear those things reverberating, you know, and it sounds like a huge tidal wave coming at you. You've got to put your little satellite, which you're holding like this, like a baby, into that thing to see whether the satellite would survive the equivalent stresses to get into orbit. So CubeSats is what I'll talk about, and then I'll talk almost not at all about my ARC training center for CubeSats, UAVs, and their applications. And I'll amuse myself by correcting Anne slightly about what UAV means for us. We were very specific to make sure that it was uncrewed aerial vehicles, not unmanned aerial vehicles. Our one little, and that is an area that we feel very strongly about. So let me move on and talk a little bit about the outline. So I'll talk a bit about satellites in space, then a bit about the space industry growth in Australia and worldwide, and why Australia should be in space. And I'll sound off a little bit about why the government wants it, which is entirely commercial, and why others of us in this room, I suspect, might want it, which are for probably other reasons, or at least, I'll put it a different way, commercial aspects are not the only important reason for doing it. Then talk about space weather and link that to CubeSats and space weather in Australia. Okay, so Anna's already introduced this very well. Of course, a satellite's just an object, natural or machine, that orbits something, and we're going to care about machines orbiting Earth in this satellite primarily, except for this slide, which shows, and I'd forgotten that Anne might talk about the Voyager spacecraft. So this is about the Voyager spacecraft, which 1 and 2 launched in 76, I think, rather than 77, but it might be 77, from Earth, moving out on their 2 paths beyond all of the planets. And you could, this outermost circle, or approximately circle, is the orbit of Neptune in particular. And now the Voyagers, which look like this, are approximately 150 to 120 astronomical units from the sun. So 120 to 150 times the distance from Earth to the sun, Earth to the sun. And we're looking at the local interstellar medium, and you can see a surface here that's intended to be the heliopause, which is the boundary, the plasma boundary between the solar system's plasma, so-called solar wind, and the local interstellar medium, with the local interstellar medium being outside and the shocked solar wind plasma on the inside. And this is one of my areas of research. It's wonderfully interesting. It's wonderful sometimes to see the space agency, the Australian Space Agency, making comments about it and using it as a justification for Australia being in space, but then intensely frustrating that the next words are always about industry. So they'll use the science when they wish to and cast it aside when they wish to as well. So I'm not going to be very political, am I? So space sector, why should we be in space research? What this perhaps rather complicated diagram is trying to show, and you're just that little bit too far away, I think, to be able to read the words, but it's the how the global space economy of about 345 billion American dollars was distributed in 2016. And you see over here, this region is about 48 billion. That's American investments, including, this is government investments, NASA, and all of the intelligence agencies in there as well. Other groups like China and Russia are in here, about 35 billion, and all the rest is commercial. So about well over 2/3 is commercial. And that ranges all the way from satellite TV to satellites, to communications, to Earth observations, various reasons that we'll come to in a moment. You might say, okay, great, that's $345 billion, a lot of money. Do I care? Well, one reason what we should care is that that is an area of industry that's growing at a rather rapid pace. So this is some data, projections from Morgan Stanley. The precise details don't really matter, except to show that they've got various colors corresponding to different areas of the space sector, and the total is obviously rising. And the growth rate there is approximately 7% per annum. And most investors very happy to get anything like 7% over the long term, and particularly so at the moment. And you might say, well, how reasonable is that? Well, if you look at the revenues from 2005 to 2017, that is what, excuse me, the growth rate was, approximately 7% per annum. And so another way of looking at it, there are predictions from, for instance, the US Chamber of Commerce that the global space industry will increase from about 385 billion roughly today to about 1.5 trillion by 2040. It's about 5% of US GDP in 2040, and growth rates of order 6%, but plus or minus 2 or so, which is attractive. And that is one of the major reasons why the current government, and in fact the previous governments back to Rudd and before, were interested in space. It's industry, it's jobs for people, yes, other uses that I'll come to at the moment, but their primary interest is economic, as probably does not surprise you at all. And the goal being to triple the Australian space sector by 2030 and achieve growth at a rather large rate, 8.5%. So why should we be in space? Well, as a scientist, I have to put this one first. I'm not sure why it's flickering on the display screens here.
You're flashing.
Yes, I don't know why, is the answer. There's a plug. Let's keep going and hope that, that things work out. So public good, blue sky, fundamental research. Here's some illustrations of thunderstorms across, in fact, in this case, in the United States, I believe. And then the sprites that one sees associated with them, which are essentially like lightning discharges, but further up. You're looking at 100 kiloamps of current and energetic, corresponding to energetic electrons. Well, okay, so wait a moment and we'll come back to that.
You were unplugged, no power, so I assume the batteries were going flat. But...
Oh no, I've got no issues with the battery. but we are getting these periodic. So another reason is commercial applications. This is the primary one. All sorts of applications, from EOS or Earth observations from space, otherwise known as remote sensing, to GPS equivalent. So global navigation system of systems, but glorified GPS, to measure all sorts of things: time, locations, predicting water and environmental needs, agricultural needs and yields, industrial output, mineral prospecting, commercial intelligence, looking at things like the number of trucks going into an Apple store, Apple factory in China, operating mines, financial networks. Most of you will know that all of our financial transactions are time-stamped with GPS signals. That gone, global financial system goes down. All sorts of other ones: internet and application communications via space assets, lots of high growth startups as well. These are mostly Australian ones actually that I'm mentioning here, except Planet Labs, which was started by one of my PhD students, and Chris Boschhausen, who some of you will know. Again, this is what we're looking at doing: improving Australia's economy. If we only bring home 10% of the amount that Australia spends on space per annum, which is $2 to $4 billion, and we use the standard economic multiplier of 5 for the benefits from direct investment rather than just buying it from somewhere else, you get $1 billion. So we're looking at bringing at least that amount home just by spending 10%, an almost trivial fraction of our money on Australian services rather than buying them from overseas. Also, huge growth rates in the small satellite business, and the idea that many countries have, including Britain, is to try and gain a larger fraction of the global space sector, especially the global space industry. And we should be trying to do that. So what do I mean by Earth observations? Here are some data of Sydney Harbour region, for instance. You can see it here with the various rivers, etc. Here's Sydney, here's Hawkesbury, etc. And you can see, you can do all sorts of things with these data. You can locate flooding events. You can look at the growth rates of trees, for instance. You can prospect for minerals, many different things. You look at hazards. You can look at the weather, climate change, security and defense matters, all the way to looking at the atmosphere changing as a function of time. And in this particular two sets of data at the bottom from a NASA satellite, it's looking at emissions from the atmosphere as a function of time, with time going this way. This is latitude here. And all we really want to do is look at the pattern here, that suddenly there's a big red spike, means lots of things happening. And that in fact was associated with the space weather effect, changing the chemical composition in a certain region of the atmosphere. So bear that in mind for the future. GPS and GNSS, you know, it's global positioning, timing, navigation, and Australia is investing a lot of money in a space-based augmentation system, SBAS, and part of that relates to the Internet of Things, where everybody's trying to connect all sorts of devices, whether they're measuring water flow in a paddock, or you know, the amount of television that somebody watches in a place in a mining camp. All relates to Internet of Things, huge commercial opportunities. So public good and national security applications, they're pervasive, and I'm not going to talk about them because I, in some sense, already have. I'm going to instead go on to talk about space weather. So this is one of the major reasons we should be in space, in my opinion. And what does space weather mean? It's the conditions in space that may affect human systems and activities in the Earth, but also in space. So astronauts care about space weather because it involves radiation, for instance, as do airline pilots going across from Australia to Argentina or Chile, for instance, when you fly over the poles. And it's related to events that could, as I mentioned before, knock human society back into the Stone Age. And we need to be able to, with our international partners, predict and then be able to mitigate large space weather events. For instance, one thing you can do quite simply in one sense with a space weather event that's affecting the electricity grid is turn off parts of the grid. But you won't do that if you don't know that an event's coming and you don't trust the prediction, because otherwise you lose lots of money involved in selling that power. So we need to have reliability, and we need then to be able to mitigate. So what am I wondering about? I'm looking at activity on the sun and the solar wind. So this picture here shows an outline of where the sun would be with an occluding or shadowing disk here. And we're seeing the weak, relatively weak light scattered off plasma, so electrons and ions in the corona of the sun. And where it's brighter, that corresponds to a larger density of particles, or a larger number of particles. So we're seeing here in a snapshot a blob of more dense or more numerous particles moving out. And this will turn out to be a coronal mass ejection. They go at roughly 1,000 kilometers a second, have roughly an Earth mass of material, and they are produced during major space weather events on the sun and cause significant effects on Earth. And what do I mean by Earth? Well, we're interested in everything from the interaction between events that come from the sun into the solar wind. They might pass over the bow shock, which protects the Earth from the solar wind. Some of that might go into the magnetosphere. That means the region controlled by Earth's magnetic field. And down low, we have the ionosphere, the ionized region of the atmosphere, and eventually the atmosphere and the ground. So all of those regions, we're looking at responses. So I thought I might show a movie that will explain this perhaps better than I can in words. So we're seeing here a view of the sun, computer projection, actually it's more a visual projection. We're going to see an event give rise to significant outburst of plasma moving outwards. It's going to move towards the Earth, which we'll see shortly. We'll see Earth's magnetic field lines. Here we see the dipole magnetic field lines. Those get broken, flipped back. It's called magnetic reconnection. Eventually, you get rise to another reconnection event here, an energetic plasma, moving back towards the Earth and giving us the aurora. We've all heard about the aurora, but the aurora is caused by energetic particles. And so that's what we're interested in. Let's just look at that once again. A picture's worth 1,000 words, perhaps especially of mine. And so I thought for a moment that I would talk about magnetic reconnection and how interesting it is, but I thought that was perhaps naive. But it does involve magnetic field lines being broken and reassembled in different regions, plasma raining down from the front and eventually at the back down into regions that perhaps are close to Earth and that we really start to care about. And of course, there's a lot of different types. And I'm not going to go through all of these. One of them just relates to disruptions of the electricity grid. So if you have a change of magnetic field associated with a coronal mass ejection, that by Faraday's law induces an electric field. That electric field can be along a power line that gives rise to a large current, which goes into a transformer, for instance, and perhaps blows the transformer, meaning you now have no more electricity going down your grid. That's one aspect. Another aspect is just the energetic particles. Might be galactic cosmic rays, but they're usually solar. Affects astronauts' safety, damages solar cells and other high tech. And we also get the energetic particles raining down into the ionosphere where they drive currents, changes of magnetic field, electric fields, energetic particles, etc. So a lot of applications, which at one level look quite simple. I'll just go through, effects, GPS, navigation, magnetic field changes, induced electric fields, currents, radiation damage, and also things like increased drag for satellites. And So, has it ever happened? Is it really truly important, or is it just an academic talking about it? Carrington event of 1859, you know, auroras down to 23 degrees latitude. They're usually at 65. These ones actually reached Hawaii, so that's even lower than 23. Large electric fields induced on telegraph wires. We didn't have the electrical power grid, of course, in 1859, but we did have telegraphs, and you got fires started because of the large electric fields and voltages, dielectric breakdown of the air, forest fires, and all sorts of good stuff. And as I said before, if we predicted that if it happened today, it would have taken out the East Coast power grid of the United States or the Chinese and Japanese ones, and the costs are, you know, $1 trillion a year type of number. So an Iraq war per year. And lest you think that really it's not relevant, you know, it's all historical. None of us are 160 years old. Well, we missed a Carrington-sized event by 1 week in 2013. And the idea there was just that the sun, of course, rotates, and the region pointing towards Earth was 90 degrees away from the direction going like this. It came out going this way rather than this way where Earth was. Otherwise, we would have had a Carrington event, and us space weather people either would be very happy in inverted commas because we would have seen a large event with lots of disruption and affected, you know, therefore funding later on, or we wouldn't have had a society to be in. And here's a much smaller one, 1989, you know, only about $2 billion of direct economic damage and roughly 6 million people without power for one night, and some of them closer to 500,000 without power for about 3 months, which in March in Quebec is not fun, a bit cold. I thought I'd just show you an actual piece of data. And so here, we're just seeing some events, and I'll show that once more. I'm wanting to look at is this event, that's a CME, and this is another word. And these guys here, these are the Cherenkov emission associated with energetic particles hitting the detector. So if you had your eyes there as an astronaut, you would be seeing these flashes of light due to those protons going through your eyeballs, giving you that light. Another illustration, you know, roughly a 2% decrease in performance of solar cells from just one event. And here's one of just looking at the currents as a function of time in various, I think this one's Canadian, during a space weather event. You're looking at something like 40 amps through your major power lines. Not a good thing. So what are we going to do about it? CubeSats, these are all about small satellites, built in cubes of 10 centimeters on a side, less than about 1.3 kilos. And here's Inspire 2, which was my baby, and which we launched into space on my grandmother's birthday in 2017, came in about 1.5 years later. And the focus here, okay, that's great. Excellent, Peter. One thing I did neglect to do was to look at put my timer on before I started. So. But this is perfect. Okay, so 2-unit and 3-unit, pretty standard at the moment, 20 to 30 centimeters tall, but they're trending bigger with time. And really the point here is that we're trying to go towards systems which are not bespoke. We've got a standard for the design. We can buy some things off the shelf in inverted commas, which really means order it and wait. And it's not just toys for the girls and boys. It's actually doing something with the asset you now have in space. The focus is not on the engineering details, but on what you can do with it. So I've gone through that. And really the point here is, do we want to do everything, or can we buy some things off the shelf? Because none of us have built our own fridge. Some of us might have built our own computers, although I'm not one of them. But you know, generally we buy things that we don't think we can make well. And so I think the important point about this slide is that CubeSats can be extremely good value. The Inspire 2 satellite, we only spent $150,000. Yes, we had to have a very difficult time raising that money, but it was only $150,000 for everything. And all of the 3 Australian QB50 CubeSats that went into orbit, which are in fact only Australia's 3rd, 4th and 5th Australian-built satellite to get into space. They each cost less than 500K, so less than a Boost Juice franchise. So very achievable amount of money for small groups, whether they're commercial or academic or government for that matter. And so it's really demonstrating the breaking of the economic barrier to Australia being able to get into space. So let's talk about satellites themselves a little bit. This is showing the 3 Australian QB50 satellites in the Wombat XL thermal vacuum chamber at the ANU, at the Advanced Instrumentation Technology Centre. We have Inspire 2 here, UNSW ECO, obviously from UNSW, and SUSAT from South Australia. Just showing we can build satellites, we can test them, they work. And we can do it. And these are just some snapshots of us reaching space. It was on a Northrop Grumman Antares rocket, 18th of April, but launched on the 26th of May from the ISS. Here's a snapshot seeing the rocket going up. And you can just see here a snapshot showing the CubeSats as they were pushed out of the deployer. Quite literally is like the Monty Python skit where you have all of these machines and which go ping when you push a button. In this particular case, you push a button, the end of a tube opens up, and then a spring at the bottom goes ping, and out it goes at about 1 meter per second relative to the International Space Station. And these are some data from Inspire 2. So you're actually lucky, you're some of the few people to have seen data from the Inspire 2 satellite. The details aren't too important, except that these are energetic particles from the sun, logarithmic scale. And you can see here some events, substantial events, up by a factor of 100 relative to the background, thousands to tens of thousands relative to the background. And this is another indicator of space weather, just looking at magnetic field fluctuations in the auroral zone of Earth. And you can see lots of variations, but these guys are the big ones. And our happy little Inspire 2 satellite, we're looking here at the current going out of the solar cells. And you can see that that goes up and down, and that's just day-night because the spacecraft's going around the Earth, into the sunlight, into darkness, etc. And so you get a oscillating function like that. This is months, and so everything looks fairly good. And these are temperatures, we're looking fairly good, and then suddenly nothing. For a month and a half, spacecraft was dead, the file system was corrupted. We managed to put it back together again, came back, and it was damaged. One of the temperature sensors was always then at 0 temperature. That's what you see here. But everything else was hunky-dory. But this was damage in a particular space weather event. Current one, it's a 3-unit CubeSat, so a bit bigger. Exploded view, you've got all of these lovely little systems which are being put together, including 4 payloads from Australia. And here's another way of looking at it, various payloads. I don't think you care about the details particularly, except that it is a bit like packing things into a tube. And here we are at ARTC again. Xuelian Bai, who's the Kuwait chief engineer, and Yung Ho Un, who's one of our postdocs, and me, and our 3-unit baby. And, oh, I took out my Australian one. Okay, so here it is inside the pod to go, and it's on the shaker. And here it is, you can see the shaker. This is, a 10-ton device that moves, a 1-ton thing back and forth with a huge acceleration. And I'm not going to show you the video of that. I'm instead going to say This one is going to go into orbit, we believe, into space on the 14th of March next year on a SpaceX launch. And here are the conclusions. Look, satellites and a vibrant space sector are really important to us. Multiple reasons. We've got to get into space as a nation, and the government has created a space agency, which is very focused on space industry. Personally, I think it needs to be broader than that, and most of the agency people agree that research is vital. Questions where you do the research. Is it in an industry group, or is it in a university, or is it both? Which is what it really should be. Space weather, really important, increasingly so as we rely upon these space assets and their data and services for everyday life. It's not something which is that rare. 1859, one large event we know about, another one in 2013 that we missed by a week. We're looking at trillions of dollars worth of economic damage, forgetting about the human cost. And one way to address it is by CubeSats, where we've used that to break the economic barrier to Australia entering the global space sector. The government can no longer say Australians can't do it. They've done it. And we at CUAV are actively working to try and create, or help create, to be more precise, that Australian space sector. So thank you very much. Happy to take questions, as I know Anne is as well.
So thank you, Ian. That's excellent. If there's anybody online would like to ask questions, then please put them up in the Q&A. And I think, Peter, you're going to tell me if there's anybody with questions from the floor. I don't have a question yet, so if there's anybody, has anyone's?
Anyone in here like to? Ross Stubbs?
Yes, we thought it would be better if you came up and then people can.
Okay, so thank you very much, Eva and Anne, for your presentation. And I guess my question arises from the fact that I was a former chair of the Space Industry Innovation Council a decade ago, and I've recently come back into space as a director of the SmartSat Cooperative Research Centre. So, I mean, let's remember that Australia had, in fact, after Woomera, had actually decided to, for good or bad reasons, to vacate its previous leadership in the global space industry, as we all know. And yet you've shown the figures, Eva, about the size of the current global space industry. It's absolutely enormous, so why were we not in it? I remember actually in 2012 sitting before a parliamentary committee in Canberra bemoaning the fact that had Australia had established a space policy, say 10 years previously, then the purchase by Optus of what became, from America, from the US, of what became the Skymuster NBN satellites for remote Australia would have generated at least $100 million of work locally in Australia. But of course it didn't do that. Now, since then, luckily, better late than never, the Space Agency has now been established and Australia is back in the space game. Also, as you've said, the technologies have miniaturised, which means it's all cheaper. Small satellites are cheaper and achievable. Even comms is starting to move to low Earth orbit. So we can now be looking at establishing capability that will be benefit to Australia. But getting to my question, to achieve any real benefit, and of course I am conscious, and I apologise for this, that I am looking at it, interested in the economic benefits to Australia overall. Normally, we would need the research developments achieved by Australian researchers just to achieve that technology readiness level of 6 or 7 to be able to be taken up by, I suppose, larger industry partners who have the money to bring it to the market. So we may be niche, but the question is, will we ever end up with the meaningful economic benefit for Australia? You've said, Eva, that you reckon it can start from the small CubeSats. I guess I'm querying that. Thank you.
Yes. Well, thank you, Ros. Yes, so I would argue we can. In Kuava, there are a number of lines of research which are intended for commercialization. They include a communications system which at least as a satellite-to-satellite link, looks as though it can get a gigabit per second from a CubeSat, to be precise, from a 0.3U of a CubeSat, with about 5 watts. We have Earth observations instruments, really hyperspectral images, which we think we have a unique slant on and will be good. And then the GPS aspects, Andrew Dempster and his group at UNSW are starting to get into GPS reflectometry, where you look at the GPS signals reflected off the sea, and you can extract from there the wave height, the wave direction, and thereby the wind direction and speed, for instance. And these sorts of things are important for cruise ship operators, obviously, but they're also important for global weather prediction, because 60% of the planet is ocean. And of course, people like oil rig operators care as well. So that's just within Kuava. Then you've got things like thrusters, plasma thrusters. You've got then the mission operations, where Jason Held and his group at Sabre Astronautics are world leading, fighting it out with a number of groups in the United States, etc. So I think the answer is yes, that we can be competitive worldwide. Some of our things will be niche, yes, but I think we can compete, as long as we don't, we're not going to take over the American position anytime soon.
Okay, thanks, Eva. I have two questions from online. The first one, and I guess you can help with this one, Eva. The question comes from David. It says, how should we deal with space rubbish? So I know already that there is not yet any international agreement on minimizing debris. So that is a bit of a problem. We do need, it's a bit like Antarctica. We do need a very, very strong set of regulations. Circular economy, I'm not sure how that works in space, although I think there's a Japanese mission that was going to, hasn't worked the first time, but to send up a tether to try and actually grab some of the space debris. So I know, Eva, you're more concerned with space weather than debris, and a lot of it, the big stuff is being tracked. So the big stuff isn't the problem. I think it's the smaller stuff. How vulnerable would a CubeSat be if it got hit with a paint fleck?
Sorry, I'm distracted here by Peter, sorry. Yes, so I would quibble, at least with the statement that we don't have a relevant international agreement. I think the UN Copuous Treaty can be argued to address that, because we're talking there about peaceful uses of outer space, and that includes being able to use it. So space debris, as I understand it, is a matter that the associated UN committees have been dealing with. Is it enough? No, because there is a large fraction of nations which are not signatories to the Copuous Treaty. So I guess that's one aspect. Is it important? Yes, it is, for the reasons that you showed. In particular, the damage to the shuttle window caused by just a fleck of paint. Sort of thing can happen to any satellite and destroy it quite easily. So yes, it is important. Is it something that just goes away? Yes, but you have to wait for orbital decay times, and at low Earth orbit, below 420 kilometers or so, you're looking at 1.5 years. If you go up to 500, 600, you're looking at 10 to 100 years. So, something needs to be done probably about the higher orbit debris. Other ways to do it, I mean, people like EOS, or Electro-Optic Systems here in Australia, they're looking at shining laser beams onto objects, and just the associated reaction force or change in momentum associated with the laser beam hitting it and being reflected is, in their opinion, enough to significantly change orbits for small bits of debris. A lot more exotic ideas out there as well.
Yeah.
So I think it is important.
And can I just add, of course, there is this graveyard orbit, in particular, the one that's about 300 kilometers beyond the geosynchronous orbits. And something up there stays for millions of years. It doesn't, it's going to stay there. So yes, it's not going to fall down, but on the other hand, if you put too much up there, there's not a lot at the moment, then it becomes an issue for certainly the interplanetary space travel. And there's been another question saying, is human travel to Mars and other planets just a distraction, given that we've now just got 3 uncrewed, I stand corrected, Eva, that is it's one thing I picked up on. But so these are robotic missions to Mars. There are 3 of them. One's just going to circulate around in the atmosphere. The other 2 will be landing. They can do a lot. And I know some of the experiments will be picking samples up and trying to actually drill down into the surface. And then maybe a second mission will come and pick up those samples and take them back to Earth. Do we need, it's very expensive having humans travel. I'm unconvinced that we need to go to Mars. Eva, do you have a different opinion?
Well, I think it depends what you want to do. So if you're actually wanting to do science or understand what's going on, then I think a robotic mission makes far more sense. It's much more cost effective. And you don't have the risks of, your astronauts dying. A lot of people, though, only want to fund space if there's a chance of them or one of their descendants going there. The human exploration aspect. It's only meaningful if the human's there. The tree falls in the forest. Does it happen? Does it matter if the human's not there to hear it? So personally, I think there's a place for going to Mars as humans going to Mars or elsewhere. I don't think it's going to happen that soon because none of them are really looking at the space weather aspects. Those radiation events, even the relatively small ones that I showed from INSPIRE, the damage associated with those is substantial for humans. The significant space weather event occurring with the astronauts on Mars will kill them in a day. Because there's no atmosphere to protect them. Same sort of thing in the moon. The first thing they would do if they get to the moon or Mars is to dig a hole and put their spaceship inside it. It's a serious omission. But coming back to the other thing about debris, space is big. Even at, looking at something at 600 kilometers, if you look at the annulus between 600 and 400 kilometers and calculate the volume, it's 4 pi r squared times delta r, and I don't remember what the number is, but it's, billions and billions, it's trillions, or much larger numbers actually, I think, of the volume of the CubeSat. And so the chance of your CubeSat hitting anything else or being hit by a piece of debris is small, really small. And so, that's why most satellites, when they're launched out, they don't hit anything, they're fine. So at one level, you need to, in Earth orbit, you need to care about it more because you've got humans there and you can track things and actually do something about it, move the space station. But, the likelihood of being hit is small.
Okay, thanks, Eva. So Peter, there's somebody to ask a question.
Yeah, hi, it's Les Copeland here. Thank you very much, Anne and Eva, for a wonderful exposition that was very, very engaging. And I was very pleased to hear you use a term of astronomical jargon that I could understand, stuff. So my question is about that stuff. Is there potential for interference with transmission and reception of data, with a lot of that material being presumably metallic or that has the potential to interfere?
Okay, so from an optical astronomy point of view, just the satellite trails, there's a huge problem. But as Eva's already said, there's a lot of space out there. And while it sounds like a lot of debris, in fact, the chances of having some sort of scattering of radio waves, for example, no. It's too close to Earth for a start, so you don't, it's not a problem. Eva, I don't know about communications between satellites. I'm not sure, that could be a problem.
I think it can be a problem both ways, actually, down to the ground as well as satellite to satellite, because the metallic debris anyway will charge up and it will reflect radio waves. And so, scintillation events, just building up the noise level. So I think it could become a worse problem than it is now. But I think at the moment, most people aren't thinking about that communications issue. They're more thinking about satellites being hit and or disturbing, the night sky. So
there was a proposal by one of the big soft drink companies to launch large reflectors as advertising. Okay, that scared astronomers and a lot of people, because they were huge sails that were going to be hundreds of meters across. That was a problem. I think the size of and the shape also of the current debris it adds a noise level, but I don't think it disturbs, certainly it doesn't disturb astronomy, and I don't think it's going to be a major problem for the moment. And then there are other things up there that are coming down. I mean, we also are supposed to be tracking asteroids. So for example, there was an asteroid discovered in 2018 that's due to have its closest approach to Earth in November, and it's only 2 meters across. Okay, so it's not going to be a major event, even if it did have a direct hit. But they're really hard to track these things. So, I mean, I've been very glib in saying we're tracking 22,000 things, or the surveillance network is. These objects are not producing light. You have to either get the reflection from a laser or an echo from a radar. It's jolly hard. It's like looking for exoplanets around other stars. You've got, they're not big and they're not bright. So it's an amazing network that's actually doing the tracking.
Okay, we have one more question, Anne.
Yes.
Thank you, Anne, and thank you, Ivor and Peter. My question is about space weather, really to Ivor. You've talked about electromagnetic effects, radiation effects. What are the other effects? Temperature, maybe? And what are the catastrophic risks are we likely to encounter, or should we be thinking about? Thank you.
Right. So, yes, I mean, X-rays from the sun, from flares, for instance, give rise to increased ionization in the ionosphere and atmosphere. And that then leads to, various plasma instabilities and heating, reflection of radio signals, etc. But more generally, if you have a large flare going, an unusually large one, even more ionization, heating of the various region, you're going to change the chemical composition. You're going to change the wind patterns as well, at least for a while. When you've got this hot blob of plasma, it's going to want to expand out. For instance, it's going to move the plasma and medium around it out of the way. So you expect that sort of effect. There are effects associated with the absorption of radiation of different frequencies. Obviously, you've got the ultraviolet light that's absorbed by ozone, for instance. If the amount of sunlight changes substantially, then you get different amounts of this photolytic dissociation of ozone, and then eventually the recombination. So yes, you can get changes in the composition of different parts of the atmosphere and changes of the winds. People have worried a bit, and you might have seen this in the press about probably more than 10 years ago, really, though, about cosmic rays and seeding clouds and thereby changing the reflection of sunlight and changing the temperature. With the idea, it's not just cosmic rays, just energetic particles. And you might remember the old experiment in physics of a cloud chamber, where you have the supersaturated fog, basically, of water, of fog, and then you put a radiation source, alphas or betas or whatever, and you see the tracks of the energetic particles through there. And it's the same sort of thing with radiation going through regions of the atmosphere with significant amounts of water vapor. You can seed clouds or seed water droplets, which therefore are clouds, and thereby change the reflection. So there's a number of aspects there that people are pretty certain that that the energetic particles don't give rise to global warming or cooling, etc., in any direct fashion. But whether there's indirect pathways for certain small effects in that region to happen, it's possible. And if you have a large enough space weather event, that's going to occur in spades. So I think my answer is yes, you can get changes in the atmosphere and the ionosphere associated with these space weather events. And one of the slides I showed you, it's the one where there were two panels and there was a red blob in one of them. That corresponded to unusual amounts of absorption by a chemical component that's not usually there.
Okay. Thanks, Eva. So we have time for one more question from someone online, and it's a fun question. So the question is, are the grand claims of life on Venus, okay, so it's not quite what they've said, but is it based on good evidence or should we be skeptical? So the paper in Nature reported on the detection of phosphine, which is pH 3. So it's a gas which was detected in the atmosphere, high up in the atmosphere of Venus, where conditions are sort of like on Earth, whereas the surface of Venus is incredibly hot, and also the clouds in Venus, there are a huge number of sulfuric acid, so it's not very hospitable to life. So the paper, I don't know, Eva, if you read the report, the paper did say that they tried to I guess, exclude all geological reasons for detecting phosphine. It was detected from two ground-based telescopes, so this is not a mission to Venus. But of course, that's already in the planning. So NASA and I think several other countries are planning to go to Venus to actually try and probe the atmosphere and see. It's interesting. They did rule out a lot of things. Does it show that there's microbial life on Venus, aerobic microbial life? I think we need a bit more. Eva, do you have any comment on that?
Well, my answer would be we should be skeptical. Yes. You know, Venus is a very difficult environment for life. You know, you've got a surface temperature which is huge, and I forget the number, but 600 Kelvin or so, maybe a little bit larger. CO2, massively dense atmosphere. So, you know, certainly it's not life that we're used to. And should we be worried about, you know, the history of claiming life on Mars based on the observations that we have? You know, a lot of people have been certain that there's life on Mars, and not just, you know, the Schiaparelli, for instance, and others many hundreds of years ago. You know, these are people who've studied meteorites that have been stones flung off the surface of Mars that get to Earth, and then down to the ground, and they've looked inside them and they see, what would I call them? Things, stuff that look like the tubes from worms, or, you know, calcifications of sea worms, for instance, and or of various things related to bacteria. And they've gone with that interpretation and they've been wrong. So I think we should be extremely skeptical about it, but you know, many of us would love it if there was life elsewhere in the universe. I mean, it really has to be there. It's a question of whether it's here in our solar system with us. And we won't even comment about whether there's any evidence for intelligent life, even in this solar system.
Yeah, which is true. And there are three sort of strategies for looking for extraterrestrial life. One is actually to send robots, like they are sending to Mars, to bring back samples from the moons. There's another way is looking for evidence in the atmosphere of exoplanets, which is what they're doing for Venus. So this Venus probe was detecting these pseudo-organic molecules in the atmosphere. Or you can look for alien signals, which is what SETI was doing. So far, I'm with Eva. We haven't got it. We haven't found anything, but I also think that it's quite likely. So with that, I think we're going to stop, and I'd just like to invite Peter Tyree, who's currently chair of the Tyree Foundation, to give some concluding remarks. So over to you, Peter.
I had sent you a message a few minutes ago. There was one person who has been standing here. I'll shorten my thing if you can let him have it. Is it a very quick one?
Okay, so I didn't get that last one. Please.
Oops,
John Doherty, thank you, Anne, thank you, Peter, and thank you, Eva. My question to you, Eva, relates to the Carrington effect, which you've highlighted as a fairly critical effect, similar to a hydraulic flood. My question then relates to my engineering colleagues who are in the area. Given you've got your CubeSats and you are advising, or the CubeSat is automatically advising of this event having occurred, two things. If I'm in charge of the power grid of the east coast of Australia, and I have my responder, my sensor, which says this is on the way, do I de-energise the system immediately? What do I do? Second thing, I'm flying across the Pacific, not many navigational aids even today. Should I ensure that I have a sextant, which means some training? Would the 787 and the 350 have some sort of bubble that I can take at Astrofix?
Great question.
I'm actually happy to answer that question.
I can't stand on the. Well, if the chair wants to take over, he can.
No. It's in my field, and I actually can tell you a real answer, but that's from an electrical engineering person in the industry. I can answer it, but feel free to go first.
I mean, yes. I mean, what we want to do is to create a reliable prediction capability tested with previous events and data to be able to decide what the probabilities are and whether or not certain power lines, etc., should be turned off. I believe my understanding is that the Attorney General of Australia has that power, and there is a group that reports to that person, which relates to this question: should they turn off the electrical grid in various circumstances, and all sorts of other aspects to do with critical infrastructure. I think one answer is we're probably not there yet, but as in having a good enough predictive capability. The Bureau of Meteorology has people, however, who can advise rapidly whether an event is on the way. What they can't do very well, in my opinion, so far, is to be able to predict the severity of the event and where it will be most important. Now let's see the second. So that's what I would say about the electrical part. And now I'm drawing a mental blank on the second part of the sextant, yeah. So I think the answer there is actually simpler because there, in some sense, you don't care about what's going on the ground. You instead have the GPS satellites, which, if they're not gone, are available. And so you can get your 3D position that way. If they're gone, then you have to rely upon what people used flying across the Pacific for the last 80 years.
Right. Okay. Thanks. Over to you, Peter.
I actually had made a comment in my closing remarks on this question, so I'll get to it in a moment. So, ladies and gentlemen, online and here at the Union University and Schools Club, today we've learned a lot. I think it's been an eye-opener to all of us to see what a massive industry space can be and will continue to employ people, not just in Australia, but globally. It is so important to have it for communications, for protection of electricity grids, and I'll come to that, for navigation of vehicles, for navigation of aeroplanes and everything else. There is no doubt that the use of space, and particularly for satellites, is going to continue to have an increasing impact on our life and all of what we do. We've learned a lot today about space junk. We've learned a lot about the thousands of bits of, or millions of bits of junk up there in the sky. We've learned that there's not just 128 million particles that, with the momentum that they potentially have, if they were going to hit something in space rather than burn up re-entering our atmosphere, it's got the potential to be a lot worse than a bullet. And we've learned that there's 800 tonnes of junk and particles up there. We've seen that space travel will expand, and we've also learnt a little bit about the Hubble telescope that I certainly didn't know about before. I think both speakers today in their unique way have complemented one another in involving us in a special bit of a future that we're going to enjoy and see in our lifetime. I made a big note in my notes here about the Carrington event, and I could talk for an hour on it, but I won't. I'll try to do it in about 1 minute. We're over time anyway, so thank you for your forbearance. But there's real-time digital simulation within the electricity networks on a global basis. And there are models that are being created from 1 minute to another, so that in actual fact, it's quite easy to close down grids in an area of major storms or a Carrington effect that might be seen as coming. And certainly there's a time that you have that you can react. But given that none of these events are likely to be absolutely spontaneous, you can close a grid down very, very quickly. And you can save the operational parameters in a storage way that you can restart a black close down. So you can close it down and everything is saved, and you simulate that in RTDS equipment. And the biggest RTDS computer in Australia happens to be in Kensington at the University of New South Wales. And people in America, it's used for doing the ETSA South Australia reconstruction. PG&E in America is a very large customer and user of it where these networks are simulated. So it really is an issue. Thank you for spotting it, but don't worry too much because someone has actually thought of it. I would like to finish off by saying we've never done this before, so apologies for the little technical hitches, and we'll learn and grow. I think we're onto a winning formula with those of you that aren't here and didn't have our wine and our sandwiches and cheese and biscuits. Eat your heart out. We've enjoyed it, but in particular, we've enjoyed it because we've had two wonderful presenters, and in our cyber and ordinary conventional way, I'd like to show appreciation to both Anne and Eva.
Thank you, Peter. I guess I get to have the last word. We've had people online interstate, so yes, it was. I'm sorry that I wasn't in the room, as it were, but this mixed method has actually allowed quite a few people who wouldn't have been able to come into Sydney to come and to hear what we had to say. So thank you to our panellists. So thank you, Eva. That's great. It's a good friend. Thank you very much to the organising and the technical staff, both from ATSI and at the club, because without you, this wasn't going to happen. And thank you to all of you for attending the event, both in person and online. I wish you all continued health and safety in these very uncertain times. Thank you and good afternoon.